Hey everyone, welcome to another deep dive video with me and Erik. This week we're looking at the Scrabble Score exercise. Erik and I both have drilling happening in the background. Both of our neighbours seem to be having some sort of works going on today, so hopefully it won't come through and you won't be able to hear it. But if you do hear a bit of background noise, apologies in advance. So we're looking at Scrabble Score. It's again a pretty simple exercise. It's representing what happens in a game of Scrabble. You make words out of a certain amount of letters, and then you calculate how many points that word has earned by the values of the different letters and by adding those up. But we're going to be looking at a lot of different ways to do it. We're going through quite a few different languages. We've got some nice pattern matching and some functional stuff. Got a bit of Rust later on. Got one of my Ruby solutions. We've got some Python. We've got a bit of MIPS Assembly. So a whole variety of stuff. Lots to cover. It's going to be a nice, fun one. And we're going to start off nice and easy with a solution in Go. This solution you can see on the screen here is probably the most basic implementation you can do of this, and it will warm us up nicely. Erik, do you want to take us through it?
Yeah, so this is a very imperative version, as you probably expect from Go, where you're defining a variable score on line 6, assign an initial value of 0, and then you loop through all the letters in the string, but you do that uppercase. So if you wouldn't do that, you would have to account for the fact that you would have lower and upper letters, so you would have double the lines of code. So just converting it to uppercase makes it a little bit easier to do the normalization. And basically, everybody that ever does this exercise does this up front. So I haven't seen anybody use both. So kudos to all of you.
Yeah, nice and simple, nice and straightforward.
Yeah. And then within the loop, you just have a case statement. In some languages, you'll have to do separate cases. So you have case A, case E, and then you might have a fall through. But in Go, you could actually do a case and then have a list of elements to match on. So that makes it slightly more ergonomic. And in this case, it's just listing all the letters that are give you the score of 1. Well, of course, you increment the score by 1, etc., etc., etc. And in the end, you return it. So I guess nothing really, really fancy here, but very readable and easy to understand.
Yeah, nice. I like the use of the word ergonomic. I'm going to use that to describe code more in future. Okay, cool. Well, I don't think we need to linger on here for very long. So let's jump straight into the next one. And this is, we're getting a nice functional solution in early. We often tend to leave those until later in the video. But today we're looking at this functional solution as our second one. Yeah, Erik, talk us through this. Bit of F# for us.
Yeah, so as often the case in functional languages, people tend to split up things in functions. So the Go version had just one big function and that was fine. But in functional language, you are usually defining things in very small-ish functions. So what the author did here was to extract the bit where a letter is associated with a score into a separate function. And it's called letter score here. They are using the function keyword, which is slightly weirdly named keyword because it's actually sort of like a shorthand for pattern matching, where you're pattern matching on a single value. So in this case, you could read this as letter score has a single parameter, and then you do a pattern match on that single parameter. But this is just a shorthand notation, so don't get confused about the naming because I'm not a fan of it myself. But then you can do something like what Go did. You can pattern match on a lot of values. In this case, they have to separate by pipes, and then you return that value. So one thing that is different here is that you have to account for the fact that there could be another letter. So not one. It could be the case that none of the letters match. Maybe there's some bug in the input. I don't know. Maybe there's a number. And in F#, the compiler will complain. And in many functional languages that you haven't handled all the cases. So as the catch-all, you could either, fail, maybe throw an exception. And in this case, they just return 0, which is, I guess it's fine. So that's just design choice. This exercise leaves it up to you. And then within the actual score function, again, converting to uppercase first. And then there's a pipe operator, where we pipe the result of the word into sequence.sumBy. And sequence.sumBy is a higher order function, where the first argument is a function that is called for on every single element in the thing that you are piping into. So word is a string, and if you pipe it into a sequence, that function that you pass into it gets called for every single letter, as you probably expect. And then sum by means, return the sum of all of those calls. So this is sort of like a shorthand for doing a map first, and then doing maybe a reduce or a sum. But now you can combine that in two. So that's a neat little trick that you can use in F#.
Nice. Do you know off the top of your head what the sum by is actually passing in? Is it like characters? Is it graphemes? We've talked about this a bit in this series. What's actually the sort of thing that gets indexed in a string in F#?
They are I think they are UTF-8 characters. So they're the graphemes, I think. I'm fairly certain that it's not runes or code points or anything like that. So they're graphemes. But.
Nice. Cool. Really nice solution. Again, nice example of a bit of functional programming. A really straightforward, readable one there. So move on now to Python. Your pitch's solution in Python. This is sort of another looping one, I guess, looking at the bottom, Erik, but with an enum this time, I guess.
Yeah, so the previous solutions were all, not directly map-based. There were pattern matching in the F# one, and the other was like an imperative version. But I would say almost the canonical solution to this exercise, at least the one that most people will use, is to define some sort of map where you put in a letter and you get back but the map is then like a thing. So the pattern matching is a function, but in this case you have a class letters, and that's using the IntEnum class. It's based on the IntEnum class, and that allows you to define a mapping between things and then mapping them to integers. So in this case, we are mapping all the letters. So there is a very concise syntax. So you can do equals, 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 and then at the end have the actual value. So this sort of defines a data structure as you would like, where you can index into an instance of that letters class, but you don't have to create that letters class actually. So that's a nifty trick here. So you see on line 25 that you don't actually have to create an instance of that letters class. You can just index into that class by character. So that's what's happened here. So you have the sum function being called, and then between the parentheses, that's a generator. So it's like creating a list, but not actually materializing it. So it has a bunch of properties that are good for performance, but also great for readability. So word.upper, of course, converted to uppercase. For C in word.upper is going over all the characters in that sequence, and then you index into that letters thingy that you created to get the actual value. So there's no error handling here too, and of course it doesn't need to because the exercise doesn't require it. But it's basically a very shorthand solution, and it's almost equivalent to the F# one, except for F# one uses a function, but this is more like a map.
Nice. Yeah, it's really nice and simple. This syntax always confuses me. The whole using brackets as a sort of inheritance thing in Python always catches me out. I always think something's been passed into something, but yeah, this is just effectively inheritance with this as a base class, right, Erik?
I think so.
Yeah. Okay. Neither of us are particularly Python experts.
Python. Sorry.
Okay, let's look at this next one then in Groovy. Talk us through this, Erik.
So this takes a slightly different approach. So previously it was all letter based, and this time it's string based. So we are defining a scores mapping, and that scores mapping has as their keys strings instead of characters. So the string AEI blah 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 is mapped to the value 1. So you don't have the commas or the pipes. So this is slightly more succinct. But the downside is that when you actually have to determine the letter scores, you can't just index into that thing. You have to first index into a value and then check if the character is in the string. So that's what's happening here. So the word is converted to a list. So that's converting to the individual characters. Then the sum method is called. it's starting out with the value 0 because otherwise it would fail if there aren't any elements in it. And then there's a lambda, like an anonymous function that says, hey, X is probably not the best name, but that's the character. So I prefer maybe C or maybe even something longer. And then it tries to find the entry in that scores mapping where the key contains the uppercase version of the letter. So that's what's being done there. So K, V are rel names, so key, values. So it finds the key value pair where the key contains the letter, and then you do dot value to get to the actual the letter score, and that is what's being used by the sum. But this is sort of a trade-off where it looks very nice in the definition, but well, it is less nice in actual execution because you have to go through all of them, and potentially it could be like the letter Z, and then you would have to do 7 comparisons before you get to that. And I would also maybe have liked to move the uppercasing to the beginning, because now for each letter, and if it was Q, you do 7 uppercases for the same letter. So performance-wise, it probably doesn't matter at all because Scrabble Score is such a limited domain. But if you were to try to optimize this, move the uppercasing to the left so that you don't have to do it within the loop.
I always think through with things like this, if you've got like some program where you're trying to calculate the Scrabble score for every word in the whole English dictionary, then actually performance starts to matter because you're running this, millions of times. I don't know how many words there are. Totally. Well, not millions, but a lot of times anyway. So it's a trade-off between, if you're just running this in a normal game, it probably doesn't matter. But if you're trying to build an online Scrabble game that's going to have 1 million people simultaneously playing it, this sort of performance actually matters because this is going to be costing you money as you have to have more servers running to do more things in parallel. So, always trade-offs to consider with this stuff, with speed.
We'll have a more performance-oriented approach later on.
Yes, we will. Some Rust, some assembly. We've got fun stuff coming up. So this is my solution in Ruby. This wasn't one you actually chose, Erik, but we looked at the Raku one coming up. It's very similar to this, but maybe this is slightly more readable. I'll let you talk people through this.
I'm going to talk through your solution. Okay, so this is sort of like a mixture between the previous versions where you still get the readability of having to define the strings without the commas and the pipes, etc. So quite succinctly, that's what's happening on line 13 to 19. So percentage W is creating a list of words. So, and those words are A, E, I, O, blah, blah, blah. So, and then mapping them to 1. But we want to be able to index it by character. So instead of having maybe some finding and string contains, what's actually happening here is that you're defining a separate class, which is well named multi-key hash. So you start with pairs, and those are lists, and those are mapped to a value. And then you're sort of, for each of the values in each, so there, letters, values. So, and then you're saying letters.product, which is a fancy way of sort of zipping them together. So all the individual elements within the letters are paired with value. So A, I, O, blah, 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 it becomes A to 1, E to 1, I to 1, etc. And then you append that to that array. You convert it to a hash afterwards. And then then later on you can index it. So this is a mixture where you still get the benefits of allowing you to index into that element list by letter. That's what's happening on line 25. So you have letters, square brackets, letter. But the definition still looks quite nicely, and it looks a lot like like a regular string. So I like this. It's different.
Yeah. What I liked about it was that this is just quite a useful sort of construct to have in general. Like I could see just having this in a sort of standard library of functions or classes that you bring into your own program. So this is very sort of multi-usable. But then, it then allows you to define this. And the percentage W you mentioned, but it just breaks a string by spaces and then turns that into an array of all of the individual things. These could be longer strings, they don't have to be individual letters. then this is just pretty straightforward. I think there's something in the Ruby test where it passes nil in one time, so you need to check that you actually have a string, which is why that happens. And there's another sort of error handling one where it has white space either side, so that's why we use the 2s and strip, which we haven't needed to do in some of the other ones. But yeah. I wrote this years ago and I hadn't seen it for a long time, but it's quite nice. I quite like it. And this shows off nicely as well Ruby's one-line methods, which came out a couple of years ago, which you can now do as well.
Which
so that's a long
named, like endless methods, I think.
Yeah, endless methods. Yeah,
it's they don't have an end.
They don't have an end.
Yeah,
but they're not really endless.
No.
So that's a 30-line version of this. This is basically the same code in Raku. Again, for a reminder, Raku is Perl 6, so it's a fork of Perl. But this is a much more concise version of the same thing. Erik, do you want to talk us through that? I'm going to make it slightly bigger. Do you want to talk us through that?
Yeah. So on line 3, you have my percentage letter dash score. That's that's defining the hash. So it's similar to what you did. And then the definition on line 4 is between the angle brackets, you have those strings. And those strings are then mapped. So that's the dot map. And star.cum means convert them to the individual letters. So at first you have a collection of strings, but then you have a collection of a collection of characters. So the first element in that resulting collection is the collection with A, E, I, but all as separate things. And then you have the special operator. So you not only have the equals greater than sign, but you also have a version where you're applying them like pairwise almost. So there is a special name, I just forgot it, but there is a special name in Raku where you can combine these operators on two lists. But this essentially means the same thing what you did. You're applying that operator to the individual values, but you have like a multi-key. So for that first list where it contains A, E, I, O, U, you're saying A, and then the equals maps to 1. E maps to 1, etc., etc. And then it does that for the second element in the list, for the second element in that other list. So that will be D maps to 2, G maps to 2. So it's doing that like if you're used to functional programming, that might be called a zip, where you have two collections and you're sort of merging them together in a fancy way. And you're basically merging them together to put an association of a key and a value pair. And that's what's in that hash. And then the actual, the summing is also quite concise. So you have convert the word to characters. So that's the dot comb. Then you do the map, and the map is just indexing into the letter score with the uppercase version of the letter, and then doing sum. So that's you see. So it is incredibly concise, but it's not unreadable, I think. So you do have to know a little bit about that special operator, so how that works. But
yeah, it's the sort of thing where if I came across this cold and I was having to maintain it, I feel like I'd have to use a lot of my mental energy to work it out. But that might not be the case when you're more used to Perl. Of course, it could just be that I'm not used to it, so things like this don't immediately feel obvious. But yeah, cool. Okay, so two quite different levels of verbosity to do the same thing. So moving on, we now have a different approach. This is in Rust, and it's one of Bob Hopp's. Yeah, talk us through this, Erik.
Yeah, so I mentioned that we would have a version that is quite tasked to have great performance. So even though maps can be incredibly fast, but they are still a data structure. So they have data associated with it, and there's a little bit of cost associated with it. So in general, the best data structure to use when you want performance are arrays. So what this approach does is it defines a single array of length 26. And you probably can guess why it is 26, because there are 26 letters. And then you use the fact that the letter A is the 0th element in the alphabet list. So if you convert the letter A to the number 0, its index, and you index into that array, you get the value 1. For the letter B, that's of course the first index, or 0 base, then you get the first index at the lookup, etc., etc. So then you can just, the one thing that you have to do is you have to convert the letter A to the number 0, and that's what's happening on line 8. So it says converted to ASCII lowercase minus 97, and 97 is the ASCII value for lowercase a. So if it was an A, you do 97 minus 97 is 0. The B would be 98, etc., etc. So that's the trick that's being used here. And other than that, it's actually quite a functional approach. So it has like a pipeline, chars, filter, mapping, and I know this is something that Bob did in other solutions too, where actually lowercasing things is only being done when needed. So you could say I'm converting the entire string to lowercase, but if it would have, I don't know, 90% of it would be letters somehow, or spaces, that would be quite wasteful. But you only need to lowercase it when you're actually doing the lookup. So that's also something to consider for performance. And then you do just a sum at the end.
Yeah. Very cool. Yeah, I mean, I find this really not readable in terms of if I want to know what the letter M is, it's like, okay, well, I'll have to start at the beginning, A, B, C, D. But super fast, super... Well, I mean, one thing I do wonder is, this is obviously happening at compile time, right? So it's a static thing. I sort of feel like you could create the array out of a more visual map. So there would be a little longer at compile time, but you would still end up with an array like this for runtime.
Rust has macros.
Which might be a bit of a...
So and you could even, if you wanted to completely optimize, you could also create the array with placeholder values for all the other characters, so that you don't even have to do minus 97. So, for example, you have an array, I think 97 plus 26, that's like 123. So you would have an array of 124 values, and then you would everything. So you have the lowercase letters, have to duplicate that for the uppercase letters, and then the rest doesn't matter because you wouldn't be indexing into that anyways. And then you could just do the map without having to do the minus 97. I don't know how much it gains you. The offset is that you have a larger array, so you might get data locality issues there. But that would be something to at least try out to see if that would help. But always measure.
You could also just, you could always also just duplicate this line and then just get rid of the two lower. And then you would have the same thing for upper or lowercase. And I think you're right, they just roll next to each other.
Unfortunately,
so you could still do... Yeah, go on.
Let me see. I think there was an issue. Because,
So then you could just take away...
They aren't consecutive. So the ASCII table isn't...
Are they not?
No. So the ASCII code for the uppercase Z is 90 and lowercase a is 97. So there are a couple of characters in between them. So that's quite unfortunate.
Yeah, bad design by the original creators of ASCII there.
Yeah, horrible.
Okay, cool. So looking at MIPS Assembly then, I know people are always a bit scared of assembly, but this really is just the same thing we've seen, Erik.
You get the scores array again. So same order, of course. And then on line 9 is where it actually starts. So Scrabble Score, that's our label of the thing that we're defining. So first we're putting 0 in $v0, which is the output. Then we're loading the value of 0x20, and we'll use that later on, into T1. And we're loading the value of lowercase a, uppercase z, and we'll be doing that for some performance thingies later on. But the most important part is the loop. So on line 16, we're loading a byte. So A0 is our input string. And we're going to keep on incrementing that to move on to the next character, which is actually what's happening in line 17. So we're loading the byte and then immediately moving to the next character so that we don't have to do that later on. And then there's a bit of a trick where you have that 0x20 to convert to lowercase. So I could try to explain it here, but it's best done visually. But there is a lowercase trick that you can use where you can see that the difference between the characters has a certain variance in it, and that happens to be 0x20, which I think is 32 in hexadecimal. So if you see a 32 with an or somewhere, you probably know that this is doing lowercasing. So oring with a value always adds something. So because it only adds, it's not an add. So you could either have the same value or you could have the same plus a little bit more. And that's why, because in ASCII, uppercase characters come first. So if you want to convert to lowercase, you have to move up, basically.
Right.
So
okay.
And oring with the value of 32 is actually flipping a single bit. So 32 is like 1, 2, 4 is, I don't know, the x bit, the nth bit. Okay. So you're basically setting a single bit. So that's being, and if you write this out, you're actually, if you have an uppercase character, it will become the corresponding lowercase character just by doing that simple trick. So if you ever see a magical value of 32, it's often converting lower and uppercase, upper to lower, that is.
So what we're saying there is, in the end of the last solution, we said, oh, it's a shame that the creators of ASCII didn't think to, leave these numbers back to back. What we're actually now saying is, by just shifting one bit in a byte representation, binary representation, then we're actually able to shift between upper and lowercase. So in a different base, it works perfectly, but when we're looking at it in just consecutive numbers, it doesn't. Have I got that right?
Yeah. So if we looked at the ASCII value for uppercase A, that's 65, and the ASCII value for lowercase a is 97. So that's a difference of 32. And if you want to, you could add 32, but if you OR it with the bit, it will still be, the lowercase will remain the same. You don't want to change the lowercase thingy, because it will already have that 32-bit set. But for the uppercase versions, you would add that bit. So you would basically add 32 only when it doesn't already have that value. So so nice. That's a neat lift.
That's cool. Let's try.
Yeah.
Yeah.
So then there are, the next two lines are basically saying, if it is lower than an A, we can stop because it's an invalid character. If it is greater, then we do the same thing. Other than that, we're going to find the index. So you do basically the minus the lowercase a value, and then you index into that scores array. I'm not sure if that's actually the proper assembly name. It's probably not. But so you get the actual score, and then you add that to what you already had. So that's store in V0, the result of adding V0 with T5. And then you loop. So that's line 23.
Nice.
Up until the last character.
Nice, straightforward. Yeah.
But it's fun to see that little upper to lowercase OR trick. And to realize that it converts it, but it doesn't change the lowercase version. So it's quite fancy.
Yeah. Yeah, the whole of that's really nice. The more I see assembly and the more I've not used it probably since university 20 years ago, but the more actually it is really readable and really nice for these sorts of things. It's fun to work with, isn't it?
Yeah, it is definitely fun.
Okay, cool. Nicely explained.
And it will be very fun.
Yeah, very, very fast. Okay, so this is Orc next. By Principle is the creator of this solution. And these last two solutions, both of them made me chuckle when you showed me them earlier, Erik. So, talk us through what's happening here.
So, on line 3, the begin is something that happens before anything is executed. So we're just setting a variable scores to 0, and then between the curly braces are things that are happening for each for the input. So there's just a single one. So we're converting it to upper first one time. We've seen it like a million times already. And then the real trick here is gsub. So gsub means substitute a value in a string with another value. So we're saying gsub, then we get a regular expression. And you'll notice that is a regular expression that matches any of the letters that have the score 1 with them associated. It says replace that with an empty string, so basically it's removing them. And gsub will alter the third input. So the word, basically you're saying remove all the single letter characters from the word. But the trick is what gsub returns is the number of substitutions. So the number of times that it actually removed a thing. So and of course, if you want to get the score for all the 0 letters, if there were like 4 of those, gsub will return 4. So you do 1 times 4 is 4, and you increment the score by that. And then on the next line, you do the same thing for the letters that have the value 2, D and G. And if there were like 3 of those letters, you would have to add 6. So you do 2 times 3, and you have 6. So I'm not sure if this is very intuitive to people. I had to look it up.
Once you see it, though, once you get it, it's really nice. Like, it's a really clever way of doing it.
It is a really, it's a very fun solution, I think.
Yeah. And if you're in languages that use regular expressions a lot, of which awk is one, then it probably actually feels relatively natural to another awk developer. But yeah, I like it. I think it's very cool.
Yeah, I think it's also a very cool solution.
So definitely a sort of unique. Similar approach. Yeah, definitely unique. A sort of similar-ish approach in a way in terms of gsubs, but that uses this is just brilliant. This is massive credit to, I think Sadia is the name of this person. Yeah, massive credit, because this is my favorite solution I've seen to this. Erik, talk us through this.
So it's doing a similar version where we have a regular expression and we're doing a replacement, but instead of relying on like the number of substitutions, we're replacing each occurrence of that one letter score with +1. So we're basically creating an equation. So if we have the word A, B, or whatever, the A would be replaced by +1, the second A also with +1, and then the B with +3. So you get +1, +1, +3. And then in the end, the trick is that they're using eval. So that's basically you're running arbitrary JavaScript now. So you're asking the runtime to evaluate the result of this string as a bit of JavaScript code. And eval is evil. I've heard that a lot of times, because it's basically not something that you would normally do, but it is a lot of fun in this little exercise. So I think the +1 is there for if you don't have any value, just to have it be evaluated to a number if it was empty. But just the idea of replacing everything with basically additions, I find it very clever.
Yeah, I love it. I have nothing really more to say about this. I just think it's fantastic. The only one thing I'd say is if you'd put the 0 in front of the value, then you could have got rid of the 1 extra character. But the other thing I like about this as well is that it's using case-insensitive regexes. So we're not even having to do the 2 upper or 2 lower or anything. But yeah, I think just a great solution. Just absolute credit to Sadia. And there's been apparently 21 submissions of these. So I don't for a second believe 21 people have come up with this uniquely. I think 20 people have gone and browsed the solutions and then gone, yes, I want this. This is mine. And copied and pasted it. So that tells you it's a little bit popular as well, that people are claiming this for their own. But cool. Those are the solutions, Erik. This was a nice little fun one. If you haven't tried Scrabble Score, go and try it for yourself. I think this is quite a fun exercise to try in a few different languages as well. It's so simple, but as you've seen, it can be done. You can make use of individual languages, different features. Again, I think this is a good one if you've not tried functional programming before. Maybe you can go and try that. It's also something for meta programming or macros that you could do a little bit in, and definitely for assembly as well. So yeah, loads of fun you can have with this.
And if somebody
if you've enjoyed watching this, please Sorry, go on, Erik.
Sorry. If somebody wants to, I would be very interested to see what would be the most performant version. Maybe try Rust and try out the different versions. I'd just be really curious. How fast can you get this to go? And what are the tricks that you're using?
Yeah. Yeah, definitely leave a comment on the video if you've tried to get some cool performant version, and let us know if you've benchmarked it even better. And also just leave a comment if you've enjoyed this. Just tell us, just give us a link to your solution. Tell us which of these you've liked the most. It's always really encouraging to hear from you. Thank you so much to everyone that does comment on our videos. It means a lot to me and Erik. And please give this a thumbs up as well if you enjoy it. That really helps us with YouTube's algorithm, and don't forget to subscribe if you've not already, so that you don't miss out on any future videos. Have fun. Thanks, Erik, for your time. Thanks everyone for watching. See you in the next video. Bye bye.